The roar filled the cockpit as manifold pressure climbed beyond anything previously attempted. 75 inches of mercury showed on the gauge. The test pilot at right field gripped his controls tighter. His P-51 Mustang was drinking experimental fuel that would change everything. Purple-dyed gasoline flowed through the fuel lines, grade 150 aviation fuel. The designation meant nothing to casual observers. To engineers monitoring from the ground, it represented revolution. The airspeed needle swept past 448 miles per hour at 25,000 feet. Radio chatter crackled between pilot and ground crew. Numbers that defied previous assumptions about Allied fighter performance were being recorded on clipboards below. This wasn't gradual improvement. This was transformation. Chemical advantage wrapped in aviation gasoline that would make Luftwaffe calculations obsolete overnight. European skies were about to witness something unprecedented. Not a new aircraft design, not brilliant tactics, but fuel that allowed existing fighters to perform beyond German comprehension. What enemy intelligence services couldn't grasp yet was the magnitude of Allied petroleum engineering achievement. German synthetic fuel programs struggled with limitations that American and British chemists had already solved. B-4 fuel powering Luftwaffe fighters barely reached 91 octane on lean mixture scales. Their premium C3 fuel approached Allied 130-grade capability, but remained scarce. Meanwhile, American refineries were producing aviation gasoline with performance numbers reaching 150. The implications stretched beyond simple mathematics. A Mustang running standard 130-grade fuel achieved 437 miles per hour at operational altitude. The identical aircraft flown by the same pilot at identical altitude, but fueled with 150-grade gasoline, exceeded 448 miles per hour. German fighter pilots who had learned to respect Mustang range and high-altitude capability were about to discover fundamental changes in aerial combat equations. Messerschmitt Bf-109G fighters, representing Luftwaffe front-line strength in early 1944, managed maximum speeds of 400 miles per hour at altitude. Focke-Wulf 190A aircraft could reach 408 miles per hour under optimal conditions. Against Mustangs running 130-grade fuel, German pilots could attempt engagement on reasonable terms. Against Mustangs running 150-grade fuel, German fighters faced fundamental disadvantages that pilot skill or tactical brilliance couldn't overcome. Understanding how this advantage materialized requires examining peacetime petroleum chemistry development. Scientists understood that octane ratings measured air-fuel mixture compression limits before spontaneous detonation occurred. Higher compression ratios generated more power from each combustion cycle. More power translated to faster aircraft and higher operational ceilings. The science appeared straightforward. Engineering required to produce high-octane aviation fuel at industrial scale proved extraordinarily complex. American aviation fuel production in 1940 centered on 87-octane gasoline. This proved adequate for commercial aviation and early military trainers. High-performance combat aircraft required significantly better fuel. British forces, desperate for any advantage against superior Luftwaffe numbers, collaborated with American oil companies developing 100-octane fuel. This became available just as the Battle of Britain commenced. Performance differences appeared immediately. Spitfires and Hurricanes using 100-octane fuel suddenly gained 30 to 40 miles per hour additional speed at altitude. Climb rates increased by 500 to 1,000 feet per minute. German pilots, who had enjoyed performance advantages with their 91 to 100-octane fuel, suddenly faced even terms. Development of 130-grade fuel provided another leap forward. This fuel, with its performance number of 130 on rich mixture settings, became Allied air power's backbone through 1943. It powered Merlin engines in Spitfires and Mustangs, Allison engines in P-38 Lightnings, massive Pratt and Whitney R-2800 radials in P-47 Thunderbolts. Production scaling accelerated under General James Doolittle's direction. This pioneering aviation fuel advocate had worked tirelessly through the 1930s, convincing military leaders and oil companies to invest in high-octane fuel development. By 1943, 17 Allied refineries were producing high-octane aviation gasoline using catalytic cracking processes perfected by French emigrant engineer Eugene Houdry. American refineries alone produced millions of gallons monthly, enough to fuel massive bomber offensives against Germany and growing fighter forces protecting those bombers. German fuel production remained bottlenecked by reliance on synthetic fuel derived from coal. The Bergius process converting German coal into aviation gasoline was technically sound but slow and resource-intensive. Even at peak production, Germany could produce only fractions of high-octane fuel flowing from American refineries. Most German fighters operated on B4 fuel, rated approximately 91 octane on lean mixture scales. Their premium C3 fuel used primarily in BMW 801-powered Focke-Wulf 190s and select Messerschmitt variants roughly equaled Allied 130-grade fuel, but remained available in limited quantities. By 1944, perhaps two-thirds of German aviation fuel production reached C3 grade. This still represented only small fractions of Allied production volumes. Grasping fuel performance requires understanding fundamental internal combustion engine principles. Octane ratings measure detonation resistance. When pistons compress air-fuel mixtures during compression strokes, temperature and pressure increase dramatically. If fuel ignites spontaneously before spark plugs fire, the result is detonation. Uncontrolled explosion rather than controlled burn. Detonation creates shock waves damaging or destroying engine components. Higher octane ratings mean fuel can withstand higher compression without detonating. Octane ratings, by definition, cannot exceed 100. 100 octane means detonation resistance equivalent to pure isooctane, the reference standard. Performance numbers measure how much better than pure isooctane a fuel performs. Fuel with performance number 150 means it withstands 50% more compression than pure isooctane before detonating. Creating such fuel required adding anti-knock compounds, primarily tetraethyl lead, and careful blending of aromatic hydrocarbons like toluene and xylene with base gasoline. British fuel chemists at Royal Aircraft Establishment tested numerous blends through 1942 and 1943, seeking optimal combinations of anti-knock performance, energy content, and manufacturing practicality. American researchers at Wright Field conducted parallel investigations, sharing data with British counterparts. By early 1943, both nations had produced experimental batches of what they designated 150-grade fuel. The designation was somewhat misleading. It implied octane rating of 150, which was chemically impossible. What it actually meant was fuel with performance number 150 on rich mixture scales, combined with 100-octane performance on lean mixture scales. This fuel, dyed purple for easy identification, underwent extensive testing through 1943. Results exceeded expectations. Merlin engines running 150-grade fuel could sustain manifold pressure readings of 75 inches mercury compared to 67 inches on 130-grade fuel. This translated directly into increased horsepower. A Packard Merlin V1650-7, the engine powering P-51 Mustangs, generated 1490 horsepower at standard military power on 130-grade fuel. The same engine running 150-grade fuel at war emergency power settings generated 1720 horsepower. In P-51B aircraft with V-1653 Merlin variants, power increases pushed output to approximately 1,600 horsepower. Flight testing at Wright Field confirmed substantial performance gains across all flight regimes. Maximum speed increased approximately 25 to 30 miles per hour at altitude. Climb rates improved by several hundred feet per minute. Most importantly, these improvements came with no aircraft modifications. The same Mustang flown one day on 130-grade fuel and the next day on 150-grade fuel became measurably faster and more capable simply because of what flowed through its fuel lines. The decision introducing 150-grade fuel to operational fighter squadrons was made in early 1944. Timing was carefully considered. The 8th Air Force, based in England and conducting daylight strategic bombing raids deep into Germany, was suffering unsustainable losses. Despite first P-51 Mustang arrivals in December 1943, German fighter forces were still inflicting heavy casualties on American bomber formations. American planners needed not just escort fighters with long range, but escort fighters so fast that German interceptors couldn't easily escape or refuse combat on unfavorable terms. May 1944 brought first operational deliveries of 150-grade fuel to England. Distribution was carefully controlled. Not every fighter group received new fuel immediately. The 8th Air Force began with select squadrons, both to manage supply logistics and evaluate combat performance. The British Royal Air Force, which had pioneered much early testing, also began equipping fighter squadrons with new fuel. Priority went to units tasked with high-speed interception missions, particularly those hunting German V-1 flying bombs beginning to terrorize London in June 1944. V-1 weapons flew at approximately 400 miles per hour at low altitude. Intercepting these weapons required fighter aircraft capable of matching or exceeding that speed at sea level or low altitude, where air density reduced all aircraft performance. Hawker Tempests and Spitfire 14s could barely catch V-1s. Mustangs running standard fuel were marginal. Mustangs running 150-grade fuel had sufficient speed margins to intercept reliably. June 18, 1944, witnessed Major R.E. Turner of the 356th Fighter Squadron destroying a V-1 flying bomb by tipping its wing using his P-51's wingtip. This demonstrated a technique used at least 16 times during the campaign. This maneuver required exceptional speed and precision to position the fighter's wingtip within 6 inches of the V-1's wing surface, then use airflow to roll the flying bomb off course and send it crashing. First widespread combat use of 150-grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force tasked with achieving air superiority over invasion beaches flew combat air patrols and bomber escorts using new fuel. German fighter pilots began reporting encounters with Mustangs, performing beyond what they had previously experienced. Luftwaffe intelligence officers collected pilot reports describing American fighters that couldn't be caught in any flight regime, that could accelerate away from German interceptors with ease, and that seemed to have power reserves defying explanation. These reports were initially dismissed as pilot error or exaggeration. German fighter pilots, intelligence officers reasoned, were tired, outnumbered, and facing mounting losses. Their reports of superior American fighter performance were surely results of stress and fatigue rather than actual performance increases. This assessment was fundamentally wrong. The truth wouldn't become clear until after the war ended. Günter Roll, a Luftwaffe ace with 275 victories, mostly achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews conducted during the 1970s and 1980s, Roll spoke about his encounters with late-war Mustangs. He recalled being shocked at American fighter performance during the war's final year. Rahl, who would later test fly captured American fighters, including P-51, P-47, and P-38 aircraft, noted that the Mustang particularly impressed him with its speed, climb capability, and high-altitude performance. What Rahl and other German pilots didn't realize during combat was that they were facing aircraft whose performance had been chemically enhanced beyond designed specifications, operating at power settings that original Mustang engineers had never envisioned. The Merlin engine, designed by Rolls-Royce and produced under license by Packard, had been engineered with careful attention to thermal limits, bearing loads and detonation margins. Running engines at higher boost pressures pushed all these parameters closer to their limits. What made 150-grade fuel revolutionary was allowing engines to operate at these extreme settings without catastrophic detonation that would have destroyed engines running lower-grade fuels at the same boost pressures. Chemistry behind this capability involved complex interactions of fuel molecules, air molecules, heat, and pressure inside engine combustion chambers. Tetraethyl lead, the primary anti-knock additive, worked by interfering with chemical chain reactions leading to spontaneous ignition. But trade-offs existed. Tetraethyl lead was toxic, requiring careful handling by ground crews. It left deposits on spark plugs, valves, and cylinder walls, increasing maintenance requirements. 150-grade fuel with its very high lead content accelerated these maintenance issues. Fighter groups using new fuel experienced more frequent spark plug fouling and increased cylinder wear. American maintenance procedures adapted quickly. Spark plug replacement intervals were shortened. Cylinder inspections became more frequent. Engine overhaul schedules were adjusted. Performance gains were judged worth increased maintenance burden. For pilots, transitioning to 150-grade fuel required new operating procedures. Manifold pressure limits were raised. Pilots had to be careful not to overboost engines, particularly at low altitudes where air density was highest. Most significantly, pilots had to learn managing fuel consumption. 150-grade fuel provided more power, but running at maximum boost consumed fuel rapidly. Escort missions to Berlin and back already pushed Mustang range to its limits. Using new fuel's full capability meant careful fuel management, knowing when to use maximum power, when to throttle back for cruise efficiency. Combat reports from summer and fall 1944 document the transformation. 8th Air Force fighter groups equipped with new fuel reported higher victory-to-loss ratios and increased ability to intercept German fighters attempting to attack bomber formations. German fighters that had previously been able to make fast slashing attacks and then escape now found themselves unable to outrun pursuing Mustangs. August 6, 1944, witnessed Lieutenant Hollis Hoagland of the 357th Fighter Group flying as part of Operation Frantic missions to Soviet air bases, encountered German fighters over Eastern Europe. Flying his P-51D named Hell's Bells and running 150-grade fuel, Hoagland engaged a Messerschmitt Bf-109 flown by Günther Schack. In the ensuing combat, Hoagland's speed advantage proved decisive. He closed rapidly on Schack's aircraft and fired a burst that damaged the German fighter's cooling system. Low on fuel and ammunition, after the engagement, Hoagland broke off pursuit and waved to the German pilot before returning to escort duties. Schack managed to belly land his crippled aircraft near German lines. For 40 years, Schack wondered why the American pilot hadn't finished him off, never realizing that Hoagland had believed he had merely damaged rather than effectively destroyed the aircraft. When historians later connected the two pilots and arranged a meeting in Germany, Schack acknowledged that the American's Mustang had demonstrated performance exceeding anything he had previously encountered. The speed with which Hoogland had closed and the power reserves evident in the engagement had been unlike previous combat with American fighters. Psychological effects on Luftwaffe pilots were significant. Already outnumbered and facing superior Allied numbers, they now confronted American fighters that seemed to have unlimited performance margins. Their tactical options narrowed dramatically. They could attempt mass attacks, hoping sheer numbers would overwhelm escorts. They could refuse combat entirely, preserving aircraft and pilots. Or they could engage and likely be shot down by Mustangs that were faster, more maneuverable, and flown by American pilots who were growing increasingly confident and aggressive. Reichsmarschall Hermann Göring, commander of the Luftwaffe, famously remarked upon seeing P-51 Mustangs over Berlin that he knew the war was lost. This comment reflected the Luftwaffe's strategic dilemma. Mustang long range meant nowhere in Germany was safe from American daylight bombing. Introduction of superior fuel in mid-1944 deepened this crisis. Luftwaffe technical intelligence eventually obtained samples of Allied 150-grade fuel from captured drop tanks or crashed aircraft. German fuel chemists analyzed samples and confirmed what Luftwaffe pilots had been reporting. Americans had developed aviation gasoline with performance characteristics beyond anything German synthetic fuel plants could produce. Some German sources suggested that late-war C3 fuel approached performance numbers of 150, but production was limited, and quality was inconsistent. Allied bombing of German synthetic fuel plants, particularly raids on Leuna and other major facilities in May and June 1944, further constrained German fuel production. By late 1944, the Luftwaffe was rationing fuel. Fighter units received priority, but even they operated under tight constraints. Training for new pilots was cut back severely. Many German pilots reached operational units with minimal flying experience, compared to American pilots who typically had several hundred hours of training before entering combat. Between January and May 1944, before widespread introduction of 150-grade fuel, American bombers suffered loss rates of approximately 3 to 6% per mission. These were sustainable but painful losses. Between June and December 1944, after introduction of 150-grade fuel and achievement of air superiority, loss rates dropped to under 2% per mission. Fighter victories increased dramatically. American P-51 groups across the 8th, 9th, and 15th Air Forces claimed approximately 4,950 German aircraft destroyed in air-to-air combat between late 1943 and May 1945, with a significant portion of those victories coming after June 1944. The German pilot force, which had entered 1944 with substantial experience despite heavy losses on the Eastern Front, was systematically destroyed. By D-Day on June 6, 1944, only 2 Luftwaffe aircraft appeared over the Normandy beaches. The Luftwaffe still possessed thousands of fighters but lacked fuel, trained pilots, and tactical flexibility to use them effectively. Technical specifications of 150-grade fuel merit examination. The fuel's lean mixture octane rating of 100 meant it resisted detonation, as well as pure isooctane when engines ran at cruising power settings. The fuel's rich mixture performance number of 150 meant it could withstand 50% more compression than isooctane when engines ran at maximum power. This combination allowed pilots to cruise efficiently for maximum range, then switch to rich mixtures at high power for combat, confident that engines wouldn't detonate even at extreme boost pressures. Handling procedures for 150-grade fuel required special precautions due to high tetraethyl lead content. Ground crews wore protective equipment when fueling aircraft. Spills were cleaned up immediately to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent accidental mixing of fuel grades. Despite these precautions, safety records were good. Industrial accidents were rare. Transition in operational squadrons required pilot training. Pilots received briefings on new fuel properties and updated engine operating procedures. Manifold pressure limits were raised. Operational guidelines specified when and how to use maximum power settings. Aircraft required no modifications. Engines, fuel systems, and all components were compatible with both grades. This compatibility simplified logistics and operations. Production statistics tell a story of industrial mobilization on scales that Germany couldn't match. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons of 150-grade fuel. Allied production across all refineries likely exceeded 200 million gallons during operational use. Each gallon required refining infrastructure, chemical additives, including toxic tetraethyl lead, quality control testing, transportation to Europe, storage in secure facilities, and distribution to dozens of airfields. American industrial capacity in 1944 operated at levels that seemed almost miraculous. Factories produced bombers by thousands, fighters by tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities exceeding Germany's total fuel production across all grades. This resulted from decades of industrial development, vast natural resources, a protected homeland safe from enemy bombers, and a workforce that included millions of women who took factory jobs to support the war effort. The Royal Air Force used 150-grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire 14Ths, Tempest Vs, and Mustang 3s and IVs received priority allocation of new fuel. RAF pilots reported similar performance improvements to those experienced by American pilots. The Tempest, already one of the fastest piston engine fighters in service, became even more formidable. Tempest squadrons achieved remarkable success against V-1 flying bombs. Between June and September 1944, RAF 150 Wing Tempests shot down 638 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Barry shot down 59 V-1s. Belgian squadron leader Remy van Lierde destroyed 44. Wing commander Roland Beaumont destroyed 31. Next most successful interceptors were Mosquitoes with 623 victories, Spitfire 14Ths with 303, and Mustangs with 232. Performance margins proved valuable in every role. Combat effectiveness of 150-grade fuel was proven repeatedly through late 1944 and early 1945. Fighter groups that received new fuel reported increased victory claims and reduced losses. By March 1945, virtually every P-51 unit was running the fuel. Combat reports from this period show overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively. When they did fight, they usually suffered heavy losses. April 1945 missions over Germany often encountered no aerial opposition. The Luftwaffe was finished, destroyed by attrition, fuel shortages, and systematic elimination of experienced pilots who couldn't be replaced. May 8, 1945, brought German surrender. The air war over Europe ended with absolute Allied air supremacy. This supremacy had many causes. P-51 Mustang long range was crucial. American pilot training was excellent. Allied numerical superiority was overwhelming. But petroleum engineering advantage that 150-grade fuel provided was significant. Purple-dyed gasoline turned good fighters into exceptional fighters, gave Allied pilots confidence, and represented accumulated technological and industrial might of nations that could outproduce, out-innovate, and ultimately outlast their opponents. Speed matters in aerial combat. Faster fighters can choose when to engage and when to escape. Faster fighters have tactical flexibility that slower opponents lack. When American fighters became demonstrably faster through combination of excellent airframe design and superior fuel, Luftwaffe tactical options narrowed dramatically. Contrast between German and Allied situations in late 1944 and early 1945 was stark. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance. German fighters often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures limiting combat capability. German pilots who burned too much fuel in combat might not have enough to return to base. Allied pilots could use full power when needed, confident that adequate fuel reserves existed for return flights. This operational flexibility had strategic implications. Allied fighters could maintain standing patrols, react to threats aggressively, and sustain operations continuously. German fighters had to pick their moments carefully, conserve fuel rigidly, and often break off combat, not because they were losing, but because they were running low on fuel. Luftwaffe pilots flew knowing every sortie might be their last, not because they might be shot down, but because there might not be fuel for another mission. Allied pilots, by contrast, flew with confidence born from material superiority. They knew their aircraft were fast, their fuel was plentiful, their support system was robust. This confidence translated into more aggressive tactics, better combat results, and higher survival rates. The story of 150-grade fuel is a story about industrial warfare. Victory belonged to the side that could produce not just more aircraft, but better performing aircraft. Not just adequate fuel, but superior fuel. Not just sufficient trained pilots, but overwhelming surpluses of well-trained pilots backed by industrial bases that could replace losses faster than enemies could inflict them. American and British fuel chemists working in laboratories and refineries never flew combat missions over Germany. They never faced flak or enemy fighters. But their work, measured in performance numbers and manifold pressure readings, helped decide who controlled skies over Europe in 1944 and 1945. Every time a P-51 pilot pushed his throttle forward and felt his Mustang surge ahead with power that German fighters couldn't match, he was benefiting from chemical engineering that transformed crude oil into fuel that made the exceptional routine. German planners had assumed American fighters would perform within predictable parameters based on aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance exceeded their calculations, sustained by fuel production infrastructure so vast and sophisticated that it represented industrial capacity Germany couldn't counter. By spring 1945, as Allied armies overran Germany from east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few units still flew, often with barely enough fuel for single sorties. Jet fighters like the Me-262 represented technological leaps forward, but they came too late and in too few numbers, handicapped by fuel shortages and absence of experienced pilots who had been systematically destroyed in combat. Final accounting shows cumulative effect of Allied advantages. American P-51 groups across all theaters flew hundreds of thousands of fighter sorties. They claimed approximately 4,950 enemy aircraft destroyed in air combat, and another 4,131 destroyed on the ground. These numbers represented not just aircraft destroyed, but also pilots killed, experience lost, and German industrial capacity wasted building replacements that were themselves destroyed before achieving strategic effect. 150-grade fuel was not solely responsible for this outcome, but it was a significant contributing factor. It represented the margin of superiority that made the difference between close fights and decisive victories. The 448 miles per hour that properly boosted P-51s could achieve represented not just velocity, but also technological superiority and industrial capacity. This is what German planners hadn't anticipated: that American fuel chemists and petroleum engineers working far from any battlefield could create weapons as effective as any gun or bomb. That purple-dyed gasoline could influence aerial combat as surely as superior tactics or better training. That the key to air supremacy over Europe in 1945 would involve compression ratios of piston engines, anti-knock properties of aromatic hydrocarbons, and performance numbers of aviation fuels that exceeded anything Germany could produce. P-51 Mustangs that flew over Berlin in early 1944 were remarkable aircraft. P-51 Mustangs that flew over Berlin in early 1945 were the same aircraft, but they were powered by fuel that made them faster, more powerful, and more effective. That difference, measured in octane numbers and performance ratings, in manifold pressure readings and airspeed indicators, was one of many differences that decided who would win the war for Europe's skies. In that decision lay the fate of Nazi Germany and demonstration of Allied industrial might expressed as purple liquid pumped into fuel tanks, burned in powerful engines, and transformed into victory one combat mission at a time.